Our next speaker is Ketan from McGill University.
If there's any lag, so please tell me. Hi everyone, my name is Ketan and I'm a PhD student at McGill University under Professor Vicky Caspi. I'm showing here today the results of multi-band observation of FRB 2018-916B or R3 using UGMRT, GBT, and chime. This work is presented in cohesion with Jacob Faber's poster, so do pay him a visit to see interesting results on polarimetry, morphology, and scintillation. So FRB 2018-916B or R3 was first discovered by chime in 2018. Then the data found a periodicity of around 16.35 days in the source, which has been refined recently by Plenary et al. To 16.33 days. This is the periodicity which we'll be using in all of our phase calculations. The source was localized to a spiral galaxy around 150 megaparsecs away and has a pretty consistent DM of around 348.8. It's the first source, first until now, the only source to be detected at the low fire band of 110 megahertz, and recently it has been detected at 6 gigahertz as well. So why undertake a multi-band study? Well, it's very well established now that repeaters are more or less narrow band sources. So to take a multi-band study, it helps us cover a wide bandwidth and estimate any frequency dependence in the activity of the source. Also look into the variation of various properties with frequencies. That involves properties like scattering, width of the burst, drift rate, etc. And then we also can look into the frequency biases that might come due to frequency biases and periodicity that might come at us being very well shown for R3 by Pastum as well and their recent publication. And also a non-detection at a certain frequency range thus provides useful constraints on emission mechanism in predictor scenarios. In the figure on the right, I show our brightest GBT detections and simultaneously the time series in the GMRT band, and we find it clearly shows that the burst is quite narrow band and there is no signal detected in GMRT. So our observations were done using 3 telescopes, GMRT, GBT, and chime. We covered around 700 megahertz of bandwidth and 0.1 in phase. And one of the epoch of GBT and GMRT was simultaneous, which provided us with lots of interesting results, which have been presented in the following slides. The lines in these plots shows the arrival times of burst in our observations. So the search of the data was done using a Spandak. It's a transit-based pipeline, which is developed by Dr. Vishal. Here I present a very simplistic picture of the pipeline. It takes input filter bank file, then it does RFI filtering, uses the Presto's RFI find algorithm. Then it uses the DQ-based search algorithm called Heimdall to look for single pulse candidates. These candidates are then sorted using a Python-based classifier on various reasons of maximum candidates per second, the clustering of candidates, etc. And then there's also machine learning employed to prioritize the candidates in such a way that the most astrophysical of them is plotted first. So this helps in the visual analysis of the candidates, which later on we use to confirm the status of it being astrophysical or not. So we detected 4 bursts in GMRT data and 1 burst and there's a 1 burst in chime around the same time period, which has already been published in Plenary et al. 2021. The burst in chime, so the burst in GMRT shows quite a bit of interesting structures. As you can see, we see a downward drifting structure at 300 to 500 megahertz range, and it's like the first wide bandwidth instantaneous detection at such frequencies. And we also see somewhat a scattering tail in GMRTB, but this can also be some unresolved structures. Interestingly, in less than 2 hours of observation for GBT, we detected around 7 bursts. And since we had baseband data for them, we performed polarization studies on the brightest of the burst in our data set. We find a flat polarization angle and 100% and the burst to be 100% linearly polarized. But for more details on this analysis, I'll refer you to Jacob Faber's poster. We de-dispersed all of our burst around the structure maximizing DM of GBTE, the highest SNR burst in our data set, and which came out to be around 348.8. So to understand the various structures which are seen in the burst, we obviously did the drift rate analysis. Again, the analysis results are the procedures and the analysis are in Jacob Faber's poster. While plotting them, plotting the drift rate and whether the central frequencies of the burst which are detected, you clearly find that there's an increase in drift rate with frequency, which has been seen for other repeaters as well, and it's now well established, showing that there might be a common emission mechanisms involved with repeaters. Probing deeper into the burst structures, we estimated the scattering timescale of the burst that they showed. The GMRT-B showed a pretty nice scattering tail. So its scattering estimation came out to be 1.7 milliseconds, which is in agreement with what has been published for this source around similar frequencies. Our values are consistent with the power index of -4, extending from the 2.7 microsecond scattering published in Marcotte et al. With FRB observation of the source. GBTE does show some high scattering, but this can also be attributed to unresolved structures in the burst. But overall, our results agree well with what is expected from the source, what is expected from galactic contribution. So to probe deeper into the unresolved structures, we did a time series autocorrelation of the burst, and out of which GBTF showed us pretty clear signs of microstructures. So the width of the microstructure was determined to be around 30 microseconds. So here on the right, I show you the 4 microsecond time resolution plot, time series of GBTF. And if you just separate out a Gaussian envelope, you can very well see that there are a lot of residual peaks at that resolution. So these are since these were detected at less than 1 gigahertz, we assume that the environment is much cleaner than for R3, thus not leading to the scattering and smearing of these structures. And this also hints on the emission being microspheric in origin. Now going on to the well-established phase frequency relationship for the source, we do find more activity in our GBT band compared to UGMRT band, since our observations were earlier in phase compared to the peak activity. In fact, we don't find any burst in UGMRT, whereas the FRB was hyperactive in the GBT band. So here, this plot beautifully shows the phase frequency relationship. This takes inspiration from the Rui Luo publication. So as you can see that all the blue or the high frequency detections are earlier in the phase, and the red and the low frequency detections are later in the phase. So since we had simultaneous observations and the burst rates of the data set, we tried to estimate the statistical spectral index of the source. The concept of statistical spectral index is given in Hubin et al. So it's basically trying to estimate the distribution of energy with frequency while taking a burst rate and the sensitivity of the telescope used in the multi-wavelength observation into account. So since we had a pretty high burst rate at GBT band compared to GMRT during the simultaneous observation, we got a higher value of statistical spectral index than what was earlier estimated by Chawla et al. For the source. But we do want to point out that our observations are earlier in phase as compared to what has been as compared to Chawla et al. So this might also hint that there's a change in energy distribution over phase. So looking into spectral energy, the burst energetics, our observation value agrees well with what has been seen for the source. Interesting thing to note is that the source has like 4 order of magnitude range in all of the energy of the burst. And obviously the low far bursts are the brightest because there's a high sky temperature and you only detect the brightest of the burst there. But interestingly, we don't see burst of same energy at higher frequencies. That might say something about the emission mechanism. Doing a comparison with SGR burst, as Marthi et al. Reported, the detections were within an order of magnitude of the energetics of SGR. But again, a distance to SGR is still not well constrained. So the plot here shows at the maximum possible distance of 11 kiloparsecs. But it does tell us one thing, that if SGR was at distance of R3, we'll not be able to detect it. So this might be a possibility that due to lack of sensitivity, we might be missing out on a lot of weaker bursts from R3 that might affect the periodicity and energy estimates. We find RM variation in our data set. Our RM value is less than what has been reported for the source. And this shows a very gradual decrease over the 2-year period of the source, which has earlier been also published in Primus et al. We don't see any relationship between RM and phase of the source, but we require more data set at different frequencies and at different epochs to make a clear confirmation about this relationship which we find between RM and phase. So presently, we are taking an even larger campaign. We are going on with a 50-hour long campaign with UGMRT. So UGMRT has a very unique capability of using two subarrays simultaneously to have observation in two bands. So we are doing observation in band 3 as well as band 5. And then simultaneously, we are doing observations in the C band of using the GPT wake tourism backend. So this plot here shows the distribution of our observations. The dashed line shows 16.33 days periodicity, and the gray shaded region shows the so-called active window, which obviously is frequency dependent. And we have tried to cover as much of the active window as possible to disentangle and understand more difference in properties of bursts. So here are some initial preliminary results from the large campaign which we have undertaken. This plot shows the one which has been generated by Spandak. So it has 4 panels. The first panel shows you the time series of the burst which was detected. Then the panel shows the de-dispersed burst, and then it shows the bow tie plot of the DM versus time plot. Lastly, we show the original chunk of the filter bank data in the file, de-dispersed and time. As you can see, we detected an extremely high SNR burst from the source. So this does help maybe just cover up the energetics. This does hint on high energetics at maybe at lower frequencies, but the analysis of the data is still underway, and we have lots of more bursts, and we'll try to present them together to give a comprehensive picture about the varying activity as well as the various spectral anomalies shown by the source at different frequencies. Okay, so just to conclude, we report here the first detections of the source in 800 to 1 gigahertz range, and we find more activity in the source in the GPT band compared to the UGMRT band, which strengthens the frequency dependence and also maybe hints on an energy distribution over phase using the statistical spectral index analysis. We observe microstructures below 1 gigahertz, hinting on the source to be, hinting on the emission to be magnetospheric in origin. And since these microstructures were not scattered or smeared out, we imagine that it has a cleaner environment compared to R1. We find an increase in different frequencies, as what has been seen in other repeaters. And we also see a flat polarization angle in source, which again challenges the precessing neutron star hypothesis that has been presented to explain the periodicity of the source. We see a decrease in DM over the 2-year period, decrease in RM over the 2-year time scale. And we also suggest that we might be missing out on a lot of weaker detections at different frequencies, which might change the periodicity estimates, but it all depends upon the sensitivity of the telescope, and that might change with future projects. We don't see any variation in DM over frequencies as well as time. But overall, we conclude that the multiband studies are definitely one of the ideal approaches to study repeaters and even one of FRBs to maybe understand the difference in activity of the source as well as the different spectral anomalies which might see at varying frequencies. I'll again encourage you to visit Jacob Faber's poster to see the results on polarimetry, morphology, and scintillation analysis in much more detail. This work was done with immense contribution of all the fellow authors, as well as help from the collaboration in general. So I'm very thankful for their help and support. So yeah, quite early, but yeah, I'm happy to take questions.
Okay, great. So we have one question already in the Q&A window. I don't think we have Ketan online, but is there anybody else online who feels able to answer a question or two on his presentation? If so, perhaps you could raise your hand. Otherwise, I think we'll postpone the questions until they come up on Slack and can be answered there. Okay, doesn't look as though we have any takers. I'll just read out Clancy's question anyway. It's actually 2 questions, I think. He says, first quick question, what's your result of alpha equals -1.6, meaning that bursts are brighter or dimmer at low frequencies? In other words, which convention do you use for the spectral index? And then Clancy goes on to say, is it also correct that if scattering is small and your source is at the beam center, you shouldn't have any bias in your frequency measurements? So we'll leave that, I think, to be answered online. And we'll move on to the next talk, which is a live presentation from Rui Luo from CSIRO. So Ray, when you're ready, please share your screen and begin.
Yeah, thanks, Elaine. Can you see my slides?
Yes.
Oh, perfect. Yeah,
okay, great.
Hi, everyone. Thanks a lot for coming. My name is Rui Luo. I'm postdoc at CSIRO-ATNF in Australia. At first, I'd like to thank the organizer for giving me this opportunity to present our work published in Nature last year, which is mainly about diverse polarization angle swing we detected from the repeating FRB source using the FAST telescope. In this talk, I will be presenting the main results on behalf of the FAST collaborations, including many colleagues and staff in NOC, Peking University, and etc. etc. In the beginning of this talk, I will review FRB repetition very briefly and tell you why we carry out the observation with FAST telescope. And later, I will let you know how we wrote FAST proposal and performed the observations. And after that, data reduction and detection will be presented. In particular, we have something new in our polarization measurements. And in the end, I will tell you, I will summarize all our contents. As we know, fast radio burst is defined as short duration radio transients with prominent flux density from its name itself. If you go beyond the name, we may find more remarkable features. For example, dispersion, scattering, scintillation, and polarization. The dispersion can exhibit as quadratic curve in the dynamic spectrum. As you can see that here's a typical FRB signal and sweeping across in the whole barriers. And the signal at higher frequency arrive earlier than lower frequency. If you remove dispersion, you may obtain the pulse profile with scattering tail, which caused by the interstellar medium. In addition, some FRB emission can be polarized. For example, we observe the very high value tension from the FRB 12E2, which is the first repeater to date. Observationally, we can classify the FRB populations two categories. The first is apparent non-repeated. That categories FRB can be observed once. Even though we use a long time for follow-up, we fail to detect any additional bursts from the same targets. And the repeaters are quite straightforward. If you observe the same source, you may expect to have multiple detection with identical dispersion measure. And at current stage, one of the biggest open question is, do all FRB repeat? And is there any intrinsic difference between the two populations? Here's the pie graph from the survey conducted in FRB 2020 meeting. As you can see that more than half people vote yes for this question. And even though we have more than 600 FRB sources in total, only 24 of them are repeaters. This debate is still very intensive. Let's look at the observational facts of the repeaters and non-repeaters. We can just plot such so-called dispersion brightness diagram, which has x-axis as extragalactic DM, y-axis as flux or fluence. And as you can see in this plot, most of those repeating bursts are located at bottom left, as well as the first time large sample. And that implies these bursts are rather fainter or lower dispersed. If you want to observe more detection, as large telescopes are necessary, and considering the sensitivity. And that's why we want to apply for observing time from the largest telescope in the world, which is FAST. And FAST has a telescope has aperture, a spherical aperture of 500 meters from its name. But its parabolic aperture is only 300 meters owing to such so-called active reflect technology. Under such design, we can change the focus of the parabolic surface in real time, which enable us to track the targets in the sky for a few hours. The sky coverage of fast telescope mainly focus on the northern sky, only a small part of the southern sky. And the sensitivity is high enough. And most importantly, this telescope has been equipped with a 19-beam receiver, which was built by CSIRO-ATNF. And this receiver have a frequency range mainly at L-band, from about 1 to 1.5 gigahertz. And the beam size at L-band is almost 3 arc-minute. And under such condition, we propose a proposal in the shared risk observation semester in 2019. And we want to monitor a couple of repeating FRB candidates, which have not been found as a repeater. They are all apparent non-repeaters. And here's the tag reports. We will only rate as grade B, and many of the referees says it's highly risky. How can you ensure detection from the apparent non-repeater? And even though you assume it's a repeater, how can you ensure the detection considering non-Poissonier process? So we will only allocate it with 2 hours for tracking. And under such limited observing time, we need to select our targets very carefully. And the main consideration is the beam coverage. For example, if you have the detection from Parkes telescope, you can just plot the beam size of Parkes telescope as 14.4 arc-minutes here. And the 19-beam of fast telescope can cover the beam size of Parkes telescope perfectly. However, you still only have 28% chance to pivot towards the targets correctly because of the gap area between adjacent beam. And thanks to the additional reminder from the Parkes observer, I finally made decision to make use of 2 hours to observe FRB 180301. And this Parkes FRB was discovered by Daniel Price in the breakthrough listen observations. And its DM value is quite normal, about 522 units, but the iron value is a bit higher than normal FRBs, which is minus 3,000. Most remarkably, this FRB has back-limited feature in the waterfall plots, which turn out to be quite unique in many of the repeaters. And our search pipeline are based on software called Burst Emission Automatic Roger, which was developed by KJ and Yunpeng. It's quite a standard single pulse search pipeline. First, you need to do RF mitigation to remove RFI as much as possible, including some narrowband and broadband ones. And later, you have to do dispersion to get the DN value of candidates. Here, we adopt so-called optimal subband dispersion. Once you have candidates, you can match filter them in a box cuff to obtain the optimal candidates. Only the candidates with high significance can be selected in the end. Here's the candidates plot we obtain from the pulsar observation. And our first observation was performed on the 16 July 2019 with 2 hour observing. In this first observing, in total, we have 4 burst detection. And all of detection happened at beam 7, which is located in the beam size of Parkes beam. That demonstrates the Parkes position is totally accurate. And the 28% chance to detect the burst really happened. That made us very, very excited. And knowing it's a new repeater, we totally proposed 4 observation to monitor these targets. In total, we have the 15 bursts from the 12-hour observations. And some of them exhibit so-called frequency downdrifting in the waterfall plots. And once you disperse the signal by maximizing the structure, you can obtain such very prominent down-frequency drifting. And some of the FRB exhibits band-limited feature. They the bandwidth is quite narrow, mainly at 1.1 gigahertz. And from the 15 bursts, we have 7 of them are very bright, which enable us to study polarization. To calculate the Faraday rotation, we adopt 2 methods. The first is to fit the Stokes parameter. As we know, the Stokes parameter Q and U following the cosine function related to the rotation measure as well as the observed wavelengths. Once we build the Bayesian inference model, we can obtain, we can input the Q and U after calibration to obtain the RM value, as well as error bar. Here's the fitting we have done for the 7 bright bursts. And to double check if the RM fitting, the Q and U fitting is correct, we still use the very traditional method called RM synthesis, which requires you have to. Thank you. Which requires you have to maximize this Faraday dispersion function with a different RM trial. Once you have the peak in this function, you can obtain the RM value as well as error bar. And the 2 RM values from the 2 methods are quite consistent with each other, but the error bar from Bayesian inference could be lower than the RM synthesis. And the RM value from different bursts ranging from 520 to 560 in units is much lower than the initial detection by Parkes telescope. And the linear polarization degree is rather high, but not 100%. It's ranging from the 36% to 80%. And the DM value from the 2 methods are quite consistent with each other, but the dispersion measure obtained by maximizing the structure can be quite stable. With the RM value measurements, we can plot the RM light curve to study the variation of the rotation measure. Here's the RM variation within a couple hours. We can find in such short term, the RM value change almost 10%, which haven't observed by any repeater before. So to double check if the trend is correct, we adopt this DM value from burst 5, which is bright burst. We can still find the very similar trends. And that may imply the very variable magnetized environment of FRB progenitor, but we don't know how to explain it in physics. And in addition, we discovered the diverse polarization angle swing from the pulse profile. Here's the pulse profile of 7 bright bursts. You can see that in burst 5, the polarization angle curve is quite flat, but in burst 9, it's go upwards. And in burst 11, it goes downwards. And in burst 12, it's even exhibit S shape. Such diversity feature have never observed by any repeater before. This discovery can help us to constrain the emission model of FRB series. And now there are 2 basic models can account for the coherent dispersion of FRB emission. The one is synchrotron measure, which requires compact objects as a central engine. The FRB can be produced by the relativistic shocks when it's propagated through the ambient medium. The other scenario is quite pulsar-like. The FRB can be produced in the magnetosphere of the neutron star or magnetar, according to the curvature radiation. And the main difference between the 2 models reflects on the polarization angle swing aspects. And we found that if you use synchrotron measure, you may expect to have the nearly flat PA curve because the magnetic field like configuration is quite all the same, far away from the central engine. But for the magnetosphere scenario, you may expect to have very diverse features, including up, down, S-shape, and even flat curve. That's why we observe such a signature in FRB 180301. In addition, this ANSCAP FRB has been detected with such feature. That's FRB 181112. And to summarize, we confirmed the new repeater from the known FRB sample using fast test scope. We discovered the diversity of the polarization angle swing, which supports the magnetosphere original FRB emission. And the ion variation may imply very variable magnetized environment of FRB progenitor. Now the FRB 180301 has been localized as a star-forming galaxy at redshift 0.33. If you want to know more, please refer to Shivani's talks in Plenary 9. That's all for my talk. Thank you for listening. I stop here and take questions.
Great, thank you very much, Ray. So we have some time now for questions, which you could, of course, type in the window as usual.
Okay.
I will wait to see what questions come in, but there is one from Jason here that's come into the chat window. Jason is asking, why do you think that repeaters typically have very flat PA curves, including your sources, but not always?
At present, I think only hand of repeater has been observed with polarization, and it's quite hard to say which one is typical. Even though we know FRB 12 we have a lot of observation on this first repeater, but that repeater is to some extent is quite untypical because of the extremely high siltation measure as well as the host galaxy. And I don't know if we expect to have very flat PA curve for most of repeaters. It needs more observations. It's still an open question.
Okay, thanks. And there's a question here from Sriharsh Tendulkar asking, not sure why the diversity of PA swings disfavors the synchrotron maser models. Could we have a diversity of emission mechanisms?
Yeah, let me go to that. Oh, sorry. Go to that plot. Yeah, this one. In this scenario, as you know, the FRB will produce when the relativistic shocks interact with ambient medium. And it's far away from the central engine. The configuration of magnetic field line should be quite all the same. If the shock wave propagates through it. As you know, this scenario requires FRB produced as the same waveforms of the shock wave. And that's even considering toroidal magnetic fields, the configuration should be all the same. You may expect to have a very, very flat PA curve. But magnetic sphere or scenario could be variable. And if you look at many pulse observation, we may have various PA curve from any pulsars.
Okay, thank you. Maybe I could ask a question also. Very interesting to hear about your experience with the time assignment committee at FAST. Will you be applying now to observe more repeating bursts with FAST?
Yeah, definitely. We have such observing plan, including the Keen Science project. Now they are observing a lot of FRB from the Chinese large sample. We aim to answer that question partially. Do all FRB repeats? We will pick the FRB with high precision for monitor targets. And if I think at least if we have a non-detection result, it can demonstrate that FRB is not active repeater, but it cannot rule out it's repeated or not. So I think the FAST is able to do that.
Great, thank you very much, and thank you for an excellent talk. It's time for us to move on now and go to the next speaker, and that is Reshma Anna Thomas from West Virginia University.
Hello everyone, I'm Reshma Thomas. I'm a graduate student at West Virginia University, and I'm also part of the Real Fast collaboration at the VLA. So today I'm going to talk about the polarization properties of FRB 190520, and these are the people I work with. So before going into the details about the polarization of a particular FRB, I'd like to talk about, in general, about polarization. So on the right-hand side, you can see an electromagnetic wave that is propagating in the z direction, and the vector n represents the direction of electric field. And by convention, polarization is referred to the direction or the orientation of electric field. And as you can see, it is inclined at an angle theta from the x-axis. So polarization can either be circular or linear. And when a polarized light passes through a magnetoionic medium, the plane of polarization, that is the plane that contains the direction of propagation and the electric field, that can rotate. And this rotation is quantified by rotation measure. And when this rotate, the polarization angle that we observe changes, and this change is proportional to the square of the wavelength. So what are the observables here, or what can we calculate from the telescope output? So we can calculate the Stokes parameters, I, Q, U, and V, where I is the total intensity, and the linear polarization fraction can be calculated using the square root of Q square plus U square divided by the total intensity. The circular polarization fraction can be calculated by the Stokes V divided by I, and the observed polarization angle can also be calculated from these Stokes parameters. So polarization in FRB, so far we have about 600 or more than 600 published FRBs, and a subset of them have polarization information. And on the right, you can see a histogram of the linear polarization fraction of all the published FRBs, and it is very evident that the one with the red outline, that is the repeaters, show large polarization angle, a large high linear polarization fraction, and with a flat polarization angle, with an exception in the repeater 180301, which we just heard, shows diverse polarization angle with inverse duration. And non-repeaters appear to show more heterogeneous polarization properties. So in this figure, you can see on the x-axis, we have the dm of the source, and on the on the y-axis, you have the rm of the source. And the distribution of pulsars and magnetars is given in the orange dots. And the repeaters are given by the blue stars and the non-repeaters by the red stars. And it is very clearly evident that FRB 121102 is an offset from this source. So of all the published FRBs, FRB 121102 has the highest reported RM of about 10 to the of greater than 10 to the power 5 radian per meter square. And from that, we can conclude that it is in the vicinity of, or it is embedded in an extreme magnetoionic medium, which is massive black holes. So we have FRB 121102 here. So before going into the polarization properties of this FRB, let me introduce this FRB to you. FRB 190520 was first discovered by the FAST telescope in China. On the right-hand side, you can see the dynamic spectrum and the time series plot of few of the bursts from this FRB. It is a very active repeater, and it has a DM of about 1200 parsec per centimeter cubed. And this FRB was localized using the real fast system at the VLA. And uh, it is co-located with a persistent radio source, which makes this interesting. And on the right, you can see the VLA radio image of the PRS. Follow-up optical observations have identified a dwarf galaxy as its host at a redshift of 0.24. Another extremely interesting fact about this FRB is its very large DM host. So for more information about this FRB, please tune into Daily's talk at the late breaking news session. You'll find more interesting information there. So is this FRB an analog to FRB 121102? So both FRBs are active repeaters. Both of them have persistent radio source associated with it, and both of the PRS luminosity is also similar. And uh, both of them reside in dwarf galaxies, and both of them have similar redshift. Both of them have very high DM host. And as we saw earlier, 121102 is uh, found to be embedded in a magnetoionic medium, but we don't know that about 190528. So we followed up this source using the Green Bank telescope at West Virginia. We did L-band observations first. We observed for 7 hours. We detected about 15 bursts. And the single pulse search was done using a package called EOR, which uses Heimdall to search for the candidates. And the candidates were classified using fetch. And on the right-hand side, you can see the time series plot and the de-dispersed spectrum of one of the brightest bursts from this observation. And we searched for polarized signal in this very bright L-band burst, and we did not detect any significant polarization. And we did a brute force RM search using the software RMFit. We did not detect any RM up to 10 to the power 6 radian per meter square. So we followed up the source using the C-band of the Green Bank telescope. We observed for 4 hours, and we detected about 15 bursts. And we searched in smaller bandwidths up to 750 megahertz. So on the right-hand side, the topmost figure shows the whole observing bandwidth, 4 gigahertz to 8 gigahertz of the C-band of GBT. As you can see, the burst that is in there is very weak because of all the added noises. Since we know that the repeater bursts are very narrow banded, it is always a good idea to search in smaller bandwidth. So as you can see on the bottom two figures, these are smaller bandwidths of the observing bandwidth, and the bursts are much stronger there. Um, and these bursts are narrow banded and they peak at different frequencies. So if we search at the whole uh, bandwidth of 4 gigahertz, then we tend to miss bursts. So sub-banded searches are important if the observing bandwidth is really large. Again, we did the search using your package, and then we classified using the classifier fetch. And we searched for polarized signal in 2 of the bright bursts from the C-band. We did a noise diode polarization calibration, and we did not detect any polarized signal in 2 of the bright bursts. And we searched for an RM, again using RMFit, and we did not detect anything significant up to 10 to the power 6 radian per meter square. And in the second observing epoch, that was 6 months later, we again observed using the C-band of the GBT. We observed for 10 hours over 4 days, and we detected 7 bursts. And again, we calibrated using a noise diode signal that was injected. Again, we did not detect anything significant in the RM search. And to verify the calibration, we observed a test pulsar, which was B1933 plus 16. And on the left-hand side, you can see the pulsar profile from our observation. The white lines shows the total intensity, the red ones shows the linear polarization, and the blue curve shows the circular polarization. And on the top, you can see an upward trend in the polarization angle as well. And on the right, you can see the published profile of this pulsar at our observing frequency. And this is from the EPN archive. Since the two profile looks consistent, and we were also able to recover the polarization properties from this pulsar, we were able to verify the calibration. So these are 2 unpolarized bursts from our second epoch of observation. One is an 18 sigma burst and one is a 7.9 sigma burst. So we have a bunch of unpolarized bursts. And what does a non-detection of polarization mean? So it could either be an unpolarized FRB, or it could be depolarized due to a very high RM. So how does that happen? That can happen due to the channelization of the bandwidth. And the intra-channel rotation is given by this, which is proportional to the channel bandwidth and inversely proportional to the cube of the center frequency. And the fractional depolarization is given by this. So if we assume, like most of the other repeaters, this repeater is also 100% linearly polarized. And if we assume a 50% depolarization, then for our channel bandwidth of 0.366 megahertz and a center frequency of 6 gigahertz, we get a lower limit for our RM to be 10 to the power 6 radian per meter square. This is pretty large. And if the RM of the source is greater than this, then we won't be able to detect anything in our observing setup. So what does this mean? From the fast data, we have a DM host. And if we assume that the DM host and the RM is from the same environment, then we can calculate the average line of sight magnetic field, which comes out to be, pretty large. So if we believe this RM to be real, our non-detection to be real, and then the DM RM picture, which I showed earlier, will change like this. And as you can see, this FRB is even higher up here, even higher than the 121102 FRB. So that makes it interesting. So that brings me to the summary of this talk. So we have this FRB 190520, which is an active repeating FRB. It is analogous to 121102 in many different ways. But we have not detected any RM so far, and we have not detected any polarization signal detection. So all these analysis is very preliminary, and we still have a lot of confirmations to do and work to do. So also for more information about this FRB, please see Deely's talk at the late breaking news session. Thank you.
So a really interesting talk. So I'm seeing a couple of questions pop up in the window. Do we have anybody online who feels able to ask them? I don't think we have Reshma with us for this session. If not, then I'll maybe just read them out briefly, and they can go online to be answered in Slack. So Ryan Shannon is asking, have you considered jointly searching for RM using all of the C-band FRBs? Or recording baseband data at L-band and coherently defaradaying the data. Sriharsh Chandorkar says, great talk and work. Is the persistent radio source found for this FRB a point source at VLBI resolution? And Jason Hessels has a question. Can't the lack of detected polarization just be due to a lack of polarized signal as opposed to uncorrected Faraday rotation? So great talk and great questions, and we'll look forward to seeing those answered online. And I think it's time now for us to move on to the final speaker for this session, and that is Henning Hilmarsson from Max Planck.
So thank you everyone for tuning in. So today I'll be talking about the polarization and scintillation properties of the repeating FRB source, FRB 2020-1124A. So first, let's look at how this FRB became really popular overnight. So at the end of March this year, an ATEL from Chime came around stating that this FRB was very active. And over the next few weeks, a lot of effort was put into observing it with telescopes all over the world. And this effort paid off, as within a few weeks it was localized with multiple telescopes. Its host galaxy and redshift were identified, and a coincident persistent radio source was discovered, which seems to be associated with star formation in the host galaxy. So the work presented here is based on two papers, one on the polarization properties of the FRB using data from Effelsberg, and one on the scintillation properties using the Effelsberg data, along with detections from GMRT. So we observed FRB 2020-1124A with Effelsberg on April 9th using the 7-beam receiver at 1.4 gigahertz. The full bandwidth is around 300 megahertz, but the bandpass drops off sharply around the band edges. So we have roughly 250 megahertz of usable bandwidth. And we recorded baseband data, so we were able to obtain coherently dedispersed archives with full Stokes information. And our observations lasted 4 hours, and we detected 20 bursts. And here we can see the massive family portrait of our bursts, where for each panel we can see the PA on top, total intensity in black, linear polarization in red, and circular polarization in blue in the center, and then the dynamic spectrum at the bottom. And the horizontal light blue lines are sapped channels. And our detections translate to a very high burst rate of 5 bursts per hour in our observing window. And we found the burst arrival times to follow a Poissonian distribution. And in many of the bursts here, we see obvious resolved scintillation patterns in frequency, which we will take a better look at later on. So here on the right, we have a closer look at our multi-component bursts. The numbers in the top left of each panel show the time and frequency resolution of the panel. And using the structure optimizing DM search code DM phase on our multi-component bursts, we obtain an average DM of 411.6 parsecs per cubic centimeter that we apply to all of our bursts. And as expected for repeating FRBs, we see a downward drift in frequency over time in many of the bursts, and all our bursts have a high fraction of linear polarization, and a few of them have a small but significant circular polarization fraction, up to about 20%. And like for most repeating FRBs, we see flat PAs across each burst. And we also note that the full width half-max burst width of our sample is quite high, with a mean width of 9.5 milliseconds, and the narrowest burst being 4.7 milliseconds. So here we can see some strong bursts from our sample that have circular polarization. And this is the first clear evidence of circular polarization from a repeating FRB. So we can compare the profiles of our sample to the Magnetar AXP J1810-197. And we see some striking similarities. So a high linear polarization fraction with small but significant circular polarization fractions. And additionally, the PAs of the Magnetar are flat to slightly slanted, similar to our sample. So we consider if the circular polarization is due to Faraday conversion, where linear polarization is converted to circular in magnetoactive plasma. So the scale of our RM changes of 10 radians per meter squared, which we will get to in a minute, and a host DM on the order of 100 parsecs per cubic centimeter corresponds to a magnetic field with a cyclotron frequency 9 orders of magnitude lower than our observing frequency. But Faraday conversion should occur when the cyclotron frequency approaches the observing frequency. And also with our low circular polarization fractions, the Faraday conversion is incomplete. So the fraction should be higher in the lower part of our band. And we don't see any evidence of circular polarization being contained within specific subbands. So Faraday conversion is unlikely, and we assume that the circular polarization is intrinsic to the source. And here we can see the rotation measure over time for our bursts. So to obtain the RMs, we used RM synthesis using RM tools. And on the left, we have the RM over time with the solid line indicating the mean RM value. And on the right, we have the Faraday dispersion function with the dotted line indicating the mean RM. And the top of each curve on the right corresponds to the arrival time of our bursts, and all the peaks are scaled to be the same height. So our RMs have an apparent variation with a mean value of -605 radians per meter squared, and their standard deviation is 11 radians per meter squared. And we also see that the bursts with circular polarization have the most extreme RM values, which are plotted in red in the left plot. So the question is whether this variation is real or that the RM is stable and the errors are being underestimated. So the errors are estimated from the width of the peaks here on the right, scaled by their height. However, if we simply fit a Gaussian to the curves and look at the 1 sigma spread on the right in red, we see that the mean RM is contained within all of them. So we hope that future RM measurements of FRB 2020-1124A will help answer this question. And if we look at the PA over time for our sample in the top panel here, we see that it is fairly stable with some burst-to-burst variation. And note that the time axis here is not in relative arrival time, it's just simply one burst after the other for clarity. And in the bottom panel, we derotate our bursts to the mean RM value instead of their individual RM values. And we see the PAs showing a bit larger burst-to-burst variation. So we can compare our findings to two other well-investigated repeating FRBs, FRB 121102 and FRB 180916B. So all three exhibit high fractions of linear polarization, a downward drift in many of their bursts, and flat PAs across bursts. And one of the many suggested origins of FRBs involves magnetars within supernova remnants, where we can use the RM as an indicator for how old the source is. And in this case, we find FRB 2020-1124A to be around a century old. And this age fits with the non-detection of an associated compact persistent radio source, similar to the case of FRB 180916B, while the presumably young FRB 121102 has an associated compact persistent radio source. And within our 4-hour observing window, we didn't find any evidence of periodicity, but that's not a surprising result given the periodicity of 16 and 160 days of the other two repeaters. And if FRB 2020-1124A is periodic in its activity, we will probably see something similar to FRB 121102, where bursts will seem clustered in time until a periodicity is found. So here we can see the scintillation spectra for our bursts. The big plot on the right shows the Effelsberg bursts over time, and the smaller one on the left shows the spectra for the GMRT bursts near the strongest detection of that observation, which is shown in blue. And we can see that nearby bursts show similar scintillation patterns, and through correlation of spectra between pairs, we can obtain a scintillation timescale. And this is the first measurement of a scintillation timescale for an FRB, which was enabled by our high burst rate. So yeah, correlating all burst pairs in their overlapping channels allows us to obtain a scintillation timescale. And for Effelsberg, all pairs of bursts were correlated. And for the GMRT, we considered only correlation of bursts with the brightest burst and obtained a timescale of 13 minutes for Effelsberg and 8 minutes for GMRT. And through autocorrelation of the spectra of the brightest GMRT burst and 4 Effelsberg bursts that span the entire band, we obtain a power law index for the scintillation bandwidth of 3.5, which is a bit shallower than for a Gaussian scattering disk or a Kolmogorov spectrum. Now, if we look at the scattering of FRB 2020-1124A, we see that it is heavily underscattered. So the plot in the upper right shows the tau dm relation for the Milky Way dm contribution. And there we can see FRB 2020-1124A as the green point. And then we also see some other FRBs and nearby pulsars with scattering measures. So FRB 2020-1124A is underscattered by a factor of roughly 20 with respect to NE 2001. So to investigate why, we looked at an H alpha map around the FRB shown in the bottom figure. And the plot is centered on FRB 2020-1124A, but we see the locations of nearby pulsars and FRB 12-1102 as well. And although H alpha emission is a tracer of ionized hydrogen and it's proportional to scattering measure, it's not directly correlated. So we can see that some of the nearby pulsars also lie in low H alpha regions, yet they fit nicely in the tau dm distribution in the plot above. A more likely explanation is that FRB 2020-1124A is towards the galactic anticenter, and the electron density maps might be overestimating the galactic dm contribution towards that direction. And the NE 2001 model is also smooth, while scattering is known to be a bit patchy. So FRBs could therefore be useful to help improving the electron density maps. So the scintillation velocity we obtain is upwards of 50 kilometers per second, assuming a scattering screen 2 kiloparsecs away from us. And this velocity is higher than the velocity of Earth, so the transverse velocity of the dominant scattering screen is either tens of kilometers per second, or the scattering screen is closer to Earth.
3 minutes.
And by measuring the And by measuring the annual variation of the scintillation timescale, we could obtain the geometry and distance of the scattering screen. So if we look at the scattering strength with distance for NE 2001, we see two possible scattering regions highlighted here in the middle with the red squares. So the top case is for a scattering screen in the second spiral arm, 2 kiloparsecs away. And the bottom case is for a scattering screen in a local environment 400 parsecs away. So the plots on the right show the measured scintillation velocities and the velocity of Earth as the dashed line. So the model predicts that scattering is dominated at 2 kiloparsecs, meaning the top case here. But if instead the scattering is at 400 parsecs, or the bottom case, then it could solve the low scattering problem, as the dm related to the scattering would be way lower, and the scintillation velocity over time is almost consistent with Earth's velocity, as we can see in the plots on the right. So for FRB 2020-1124A, we see some of the typical markers of most repeating FRBs. High linear polarization fractions, downward drift in frequency over time, and flat PAs across burst envelopes. And interestingly, we also see small but significant circular polarization fractions in a few of the bursts, which is a first for a repeating FRB. And we see a variation in RM over time. However, it is yet to be determined whether this variation is intrinsic to the FRB or if our RM errors are being underestimated. And we were able to measure a scintillation timescale due to our high burst rate, which is also a first for an FRB. And finally, we see that FRB 2020-1124A is underscattered by a factor of 20 with respect to NE 2001. But this could be the result of electron density maps overestimating the galactic dm contribution towards this line of sight. Or alternatively, this problem could be solved if the scattering screen is around 400 parsecs away. So yeah, that's all I have. Thanks for your attention.
Excellent, thank you. So I don't think we have Henning online. Are there any collaborators or colleagues online who feel able to answer questions? If not, I would encourage you to post your questions in any case, and as before, we'll get them answered on Slack as soon as we can. Okay, I don't see any questions at this point. So I think that brings us now to the end of this session on repeats and repeaters. Found it really interesting. Many thanks to all of the speakers for preparing such excellent and timely talks. Thank you to the organizers, and we'll look forward to seeing everybody at the next session. Thank you very much.